Hello, everyone. My name is Tony Lau.
Hi everyone, my name is Alvinson.
Hey guys, my name is Cesar Hernandez.
Hi everybody, my name is Erfan Mars.
And my name is Walter, and today we'll be discussing the topic of our project slash presentations, diffusion models. You might be wondering, what are diffusion models? Well, in order to understand diffusion models, we first have to discuss what are generative models. Generative models are machine learning models that create new data similar to its training data. They come into two different types. Unconditional generative models are models that generate images from noise only. Thus, outputs could be random. What this means is that when you input an random input, aka noise, into the model, the outcome of the model ends up being completely random. So, for one test run, it might produce an image of a dog, but in the next run, it will produce a different type of image. Uh, that's because the model isn't trained properly. As such, it can only make a substance of what the noise might be. This is in stark contrast to conditional generative models. They generate images from prompts and noise. What this essentially means is that in this case, when you input like a type of prompt, which could be text, images, labels, or other criteria, um, it will pass through the model, and the generative model will produce the same information that the input is asking them to. So if you give, for example, an image of a dog, the outcome to still be that same image of a dog. A good example of a type of generative model is actually ChatGPT. ChatGPT um, allows you to insert text prompts, or yeah, I think in their most recent premium models that you have to pay for, um, images slash documents, and what it produces is essentially a response to your input. So basically, if you ask ChatGPT to give you a list of all prime numbers, it will probably produce a list of all numbers based off the training data they use during its training. So that's what conditional generative models are. Now, when it comes to diffusion models, they're a type of generative models that generates images by iteratively removing noise from randomly initialized noisy images. Now, diffusion models have seen an uptick in popularity in recent years, with various platforms allowing users to produce images with text prompts and descriptions. For example, inputting written prompts to produce images ranging from completing unfinished works, transforming one image to another, and etc. For right now, we're just going to give you a overview of diffusion models. We'll definitely go into details later, which will be outlined in our plans later on in the slides. Now, when it comes to the inner workings of a diffusion model, it consists of a forward process, also known as a diffusion process, and a reverse process, known as a reverse diffusion process. Now, the forward process is when the image is continually applied with a Gaussian noise until the image is nothing but static noise. And then the reverse process is taking that same Gaussian noise that we applied earlier and reversing it, thus recovering the original image. As we can see in the image provided here, we have a picture of a dog, and then during the forward process, we continuously apply Gaussian noise until it becomes a static image, as we see on the right. Reverse process essentially takes that static image and tries working backwards in order to produce the same image as we started. Now, these processes are important during the training process, feeding the model images to distort and recover in order to build the recovering aspect of the model so that it can create new data from user prompts. So what that basically means is that when it comes to the training of these models, what we're mainly focusing on is this recovering process, aka the reverse process. So that way that when it comes to when the diffusion models comes into play, the user could just input a prompt and then the model itself will take the user input and essentially create new data from that input based off the training data that it's received. A diffusion model also uses something called a UNet architecture. It's a convolutional neural network architecture that uses an encoder-decoder structure to segment images. Furthermore, we have something called a latent space. It's a lower dimensional space for an encoder, typically a pre-trained one from a variational autoencoder, also known as a VAE. It's used by latent diffusion models or LDMs to be trained on bigger data without taking up too much time.
Okay, so on the last slide, like we discussed about like the overview of the diffusion models. Now here's a couple, like 2 examples, like how diffusion model works. So like for the right the picture on the right side, we just like simply input like a hood figure looking out towards the expanding wilderness from a mountain cliff. So when we are using a platform like Stable Diffusion, this model can like generate like high detailed image, which just from your words, like you can see like the detail of the mountains and then the detail of the cape of the like hood figure. So for the other example, which is a cat wearing a ghost costume, this this proves like how realistic the Stable Diffusion models can be. Like it can generate something realistic, but also be creative at the same time. So like this kind of like examples like shows just how like versatile like these models can be. It can just like creative, like create something realistic and creative using the diffusion models just by inputting like a simple text description of the picture you want to create, which why like this capability makes diffusion models so popular today nowadays. So like because when you are creating artwork for project or videos and stuff, usually they will hire like artists to do like pictures and stuff, or just look for like picture that fits your description online. But now you can just like type what you want to be in the pictures just using this diffusion model, and it generates like perfect art for you. So now we're gonna talk about the plans for our project. So we aim to like conduct a in-depth review of how diffusion models operates, which involves a like a detailed exploration of the system and process like behind this model, which help help us all to understand the mechanics that allows diffusion models how they can generate high quality images. So we're also going to be setting up like small scale diffusion models ourselves, which we will like develop a simple program and then showcase how diffusion models works. And then also we will analyze the pros and cons of the diffusion models, which of course highlights their strength. Like for example, like why they can produce like such high quality output or such flexible conditions, as well as the cons, like large model sizes or high computational costs. And then at last, we will compare the diffusion model with other popular generative models like transformer space models. Like this comparison will like help us understand like how diffusion models like can what's different from like performance, like output quality, than other models.
We briefly provide an overview of how a typical diffusion model operates and some of the key terms that are commonly used in discussion. We are going to use variational autoencoders. Using one in our diffusion model helps the network focus on important aspects like facial features. We would be also using datasets of images with text description for each image, which requires numerical representation of the text. The attention operation will play a significant role in text embeddings, which would allow for conditional text-to-image diffusion. Next, we'll be also talking about setting up a small-scale diffusion model. In our project, we'll be utilizing PyTorch, which is an open-source machine learning framework. We will have two different programs to showcase our diffusion model. The first program, which will have randomly generated data as its inputs, and the second program will have custom images chosen for its inputs. Both programs are very simple, meant to showcase how the diffusion model works in the simplest form. We would also be showcasing the lines of code in our program.
Pros and cons of diffusion models. Diffusion models have benefits and negatives depending on their usages. Benefits for the uses of diffusion models are high quality outputs from generating high quality images from low quality sources and enhancing specific features in an image such as colors, textures, and more. However, the quality of results may vary depending on the input data that the microparameters use. Stable training. Stable training can be helpful as to delivering the uses of noise into an image by gradually removing the state of order to disorder for diffusion. And reverse diffusion is also a form of stable training, such as performing the inverse of forward process, start from random noise and progressively move the synthesized image that matches the provided text stages. Flexible conditioning, meaning that you could transform from a quality image from a low quality image, depending on the usages. The negatives for the uses of the diffusion model is large size model size, meaning it requires more of a powerful computer such as better processor, better RAM, and better all around computers to make the performance of real time performance from an image from high quality to from a low quality image. And the computational is expensive to to emulate, basically, and it could depend on what you really want to do with the model. It's important to acknowledge how diffusion models strengthen and weaknesses in order to inform those wanting to utilize diffusion models in their own programs to play to its strengths and compare whether it's the best choice. And all in all, there is pros and cons to diffusion models, and how you portray it is depending on what images you want to compare to, from low quality image to high quality image.
Other generative models besides diffusion models include generative adversarial networks, variational autoencoders, transformer-based models, autoregressive models, and flow-based models. It's important to understand that diffusion models aren't the only generative models out there. As such, we should delve briefly into the other generative models available. Each model has pros and cons and use different algorithms and methods. For example, generative adversarial networks used to be the highest quality image generator. However, diffusion models have recently started to outperform the output of generative adversarial networks. Other differences include diffusion models only training their reverse diffusion compared to variational autoencoders, which train both their encoder and decoder, which is basically their version of forward and reverse diffusion, respectively. Basically, diffusion models are training one model, while variational autoencoders are training two models. Diffusion models use something called a Markov chain, which basically means that when they are generating the next image in the next time step, they only use the information. They really only need the information of the current time step. And then they do that gradually over and over until the final image with no more noise. While generative adversarial networks and variational autoencoders just do it all in one go. They usually call that a single forward pass. They change all the noise all at once. Variational autoencoders have two parts, as mentioned before, an encoder and a decoder, and it works differently from generative adversarial networks, even though both models do remove all the noise in one go. And they are generally faster than both diffusion and generative adversarial networks. It uses an encoder to output a mean and a variance for many latent variables using the model's latent space. Usually, the amount of latent variables sampled is the same amount as the amount of dimensions of the latent space. Those latent variables are formed into a latent vector, which is given to the decoder to generate an image based off of their collective information.
These are the references that we are going to use during our group project in order to not only develop the programs that we outlined earlier in the slides, but to also understand the overall complexity of a diffusion model. So we have two videos discussing how diffusion models work and how to create them. Two websites which are articles discussing diffusion models, and then we have the two generative AI images platforms that we use for our example earlier, just to highlight how the outcome of these models work. These references are going to continuously grow throughout the remainder of the project as we further explore diffusion models and where we learn the information from, so that other people who would like to learn more about diffusion models can look at these links and watch and learn for themselves, or play around with the models. We're also going to be including the programs so that people can have it on their platform and mess around with it. And that's the end of our presentation. I thank you for listening, and I hope you have a good day.